My name is Dr. Chris Murphy. I'm a lecturer here at the University of York, and I lecture first year undergraduate maths, and I also lecture postgraduate students in fusion energy. And I'm also the year tutor for foundation year. So as well as my teaching responsibilities, I'm also a researcher involved in high intensity laser plasma interactions. And most of my research involves something called Wakefield acceleration, which is a way that we can accelerate charged particles, particularly electrons, using plasma waves. This means that you can make accelerators much smaller than conventional accelerators, by about a factor of 1,000. So in theory you could compress something that's a kilometre long down to 1 metre. The problem is it's not very stable, and so that's where research comes in. I always think that the best thing about research is not the solutions, but actually finding the problems and working out ways to attack them. And since this is clearly something that could be important for science applications and medicine, if you imagine, Wakefield acceleration is a way of generating coherent waves inside a plasma. In fact, I've got a video that I can show that one of my PhD students has made. And in this video, you see the laser travelling from left to right, and at some point the simulation box will move along with the laser pulse. So as the laser pulse moves, it generates waves behind it, just like a boat would if it was travelling through a still pond. And you can imagine that because these waves are moving along with the boat, or in this case with the laser, charged particles can be injected in here and be accelerated. The advantage of using a plasma is it's already ionised, and that means that you don't have the same problem as one would with conventional accelerators, where if the field becomes too strong, the material breaks down and electrons become free. A plasma already has lots of free electrons. In my research, I'm an experimentalist, which means most of my time, if possible, I spend going to visit national labs that have large, high-powered lasers, and I use these ultra-short pulse lasers in order to focus them into a gas. Then the gas turns into a plasma, generates these waves, and the waves are used to accelerate the particle. So really, the eventual goal of the community's research is to produce compact accelerators that we could use for either medicine or nuclear physics or sources for security applications as well. For most people, becoming a lecturer in physics would imply that you did an undergraduate in physics, but that's not true for me. My undergraduate was done at the University of Glasgow, and it's an MSci in chemical physics. So the chemical physics course was about 2/3 of a physics course and 2/3 of a chemistry course pushed together, and given a master's as an undergraduate as a result. It was interesting. I think it's important to understand that you don't really have to stick with the particular specialty that you choose for undergraduate. One of the strengths of the course here at York is that all the courses are IOP accredited, which means that they would be accepted to go on to choose any specialism as a postgraduate option.
Brilliant.